polysaccharidases, example will be amylase, the enzymes that can break down the bigger carbohydrates. Which and their digestion will start where? In the or saliva, in the oral cavity. Correct? That's what you're telling me. Okay. So, but the digestion of disaccharides, the ones that have two monosaccharides, they're made up of two monosaccharides, like the lactose, the sucrose, the what's the other one? Lactose, sucrose, maltose, right? Maltose. Those are the disaccharides, correct? They are made up of two monosaccharides. Those ones, digestion takes place where? In the intestine, duodenum, right? Not, doesn't start in the mouth because the disaccharidases are where? In the small intestine. Okay. So where are the sources of amylase? Amylase, we have salivary amylase, we have pancreatic, right? Amylase. Okay. Which will break down the polysaccharidases. Where will it break them down? It breaks them down in the lumen, right? Of the of the GIT. Okay, oral cavity for the for the salivary amylase. The pancreatic amylase does that in the lumen of the duodenum and the jejunum, right? Which is where the pancreatic enzymes are secreted into. So that's good. Oh, okay, beautiful. Now, where are the disaccharidases? Where are they? Where are they? Where are they made? Where are they located? Disaccharidases are made by what? By the enterocytes. And they are embedded on the what? On the membrane of the enterocytes. Do you see where we get it? The polysaccharidases enzymes are in the lumen because they are secreted into the lumen. So digestion of polysaccharide takes place in the lumen of the GIT. Digestion of disaccharidases will take place of disaccharides, sorry, will take place on the surface area, right? On the surface, literally on the mucosa of the enterocytes in the small intestine. Because the disaccharidases are on the mucosa. They're like anchored to the membrane of the enterocyte of the small intestine. Why is that important? It's important to know this because if a patient has problem digesting and absorbing carbohydrates, or a patient has a lot of malabsorption, right? Malabsorption. Malabsorption, they can absorb carbs or nutrients generally. And I want to know where the pathology is. I want to localize the pathology to, right, to a particular organ. Is it on the surface of the small intestine, like the enterocyte surface area? Is it a surface area issue? Something damages like celiac disease, for instance, Whipples, things like that. Or is the problem on in the pancreas? Something's wrong with the pancreas. So the pancreas has failed, cannot release amylase. I can check the type of carbohydrate I have, right? Or the type of carbohydrates the patient has in their feces. You can check. So if I don't see any polysaccharide in the stool of the patient. What is accumulating are disaccharides only. That's what accumulates in the stool. Then the patient has problem breaking down disaccharides, right, to monosaccharides. The problem must be on the surface area, on the surface, on the mucosa, right, of the small intestine. It's not a pancreatic issue. It means that there's not a salivary issue. There's salivary amylase, Yes, pancreatic means breaking down the polysaccharides into what? Disaccharides. But patient cannot break down disaccharides to monosaccharides. So it's the mucosa that's affected. Now my differential will be what? Like small small bowel bacterial overgrowth or small intestinal bacterial overgrowth covering the surface of the small intestine, or celiac disease. Or patient with diarrhea. Sometimes severe diarrhea like gastroenteritis can dislodge those disaccharides. Yeah, from the mucosa. But if I check the stool of the patient and I see polysaccharides in the stool, but every right, so you give them a diet that is rich in disaccharide, only disaccharide diet, and the patient was able to digest it and absorb it, no problem. You give them a meal that is rich in polysaccharides, patient was not able to. It's develop severe diarrhea because they cannot break down the polysaccharide. And you know it's likely a pancreatic issue. Something's wrong with the pancreas. There's no pancreatic amylase or salivary amylase to break down the polysaccharide. Are we on the same page so far? I didn't get that. Come again. Right. Yeah. If they cannot, so yeah, so you give them a diet rich in disaccharide, they develop diarrhea. You give polysaccharide, they still develop diarrhea too. Right. Because remember, polysaccharide will be broken down to disaccharides, but they cannot break. Right. The not definitely is the mucosal surface where the problem is. Yeah. So if we successfully break down disaccharides into monosaccharides, like you mentioned already, by lactase, sucrase, maltase, the dextrins, etc., they break down all those disaccharides into monosaccharides, and the monosaccharides can be what absorbed, right, into the blood. So we can only absorb carbs in the form of what? Monosaccharides. We can't directly absorb disaccharides or polysaccharides, right? How and what are the monosaccharides we absorb? Fructose, galactose, and what? Glucose. Are the monosaccharides that we absorb. How do we absorb them? SGLT1. Beautiful. Thank you very much. Sodium glucose co-transporter, which is a transporter that is a secondary, right? Active transporter. Why is it secondary? It doesn't use ATP directly, but depends on what? Sodium potassium ATPase, which is ATP, right? Directly. So secondary active. So the sodium gradient generated by sodium potassium ATPase will allow, right, the absorption of sodium into the enterocytes and glucose will follow. SGLT1. How do we absorb galactose? Same transporter, SGLT1. How about fructose? What about fructose? So, okay, I didn't get that. We use, okay, so for fructose glutes, 5. So it's passive, right? Or fasted diffusion, which type of, right? So that one doesn't depend on energy, all right? Glutes 5, fructose, okay. And then that's the luminal membrane, right? Those are some on the basolateral membrane. They now use what? By the time you get all those guys in, you can now use two, right, on the basolateral membrane to get them into the blood, right, or interstitial, right, through passive, right, diffusion, yeah, or fasted diffusion. All right. A patient may also have, and remember, so we talked about patient having malabsorption due to problem with there's no polysaccharide disease or there's no disaccharide disease. Patient may have malabsorption because we cannot reabsorb the monosaccharides themselves. It's all possible. Because instead of testing those transporters directly, I can test them indirectly by giving an experimental question. I give you a patient that is able to absorb. So we give them, let's say you give a patient lactose. Lactose is both glucose and galactose, correct? So I gave the patient lactose and the patient did well. No problem, no bloating, diarrhea, nothing. Which means from the level of disaccharide, I have the patient has lactase and they have what SGLT1. But now you give the patient fruit, you give them fruit juice, which contains sucrose, and the patient developed diarrhea, bloating, etc. Now you're thinking they tolerate lactose, lactase is fine, SGLT1 is fine, but they can't tolerate sucrose, which means the patient doesn't have sucrase enzyme or patient does not have GLUT5 because sucrose is what? Fructose and glucose. If the examiner wants to narrow it down further, the examiner can say you give sucrose, so we gave lactose, patient tolerated it. Gave sucrose, patient did not tolerate it. I now gave them glucose, patient tolerated it. You gave them fructose and the patient tolerated it. Right. Now that rules out GLUT5 problem. It must be sucrase, right? Deficiency. Does this make sense? Right. So yeah, because they're not going to tell you directly, oh, what is the transporter for this? It's too direct. They're going to give you that kind of question like, okay, patient tolerated this, cannot tolerate this. Yeah, but you will now work it down. Okay, for me to reabsorb this guy, I must get through. Okay, if I'm starting at the level of polysaccharide, you must work your way down. Okay, I'm starting with amylase down to disaccharides. I now have my disaccharidases, and then when I have my monosaccharides, I have my what transporters. So depending on the level where the problem is or what the patient cannot tolerate, you can figure out where the pathology is in that patient. All right, let's talk about lipid. How do we absorb lipids? Oh, okay, right, right. Before you even get there, right? Okay, so tell me, what kind of lipids do we have in diet? What type of lipids are possible in our diet? Can we have? You can have, right? You can have lipids in form of triglycerides, correct? Yeah. In diet, we can have lipids in form of triglyceride, which are basically what, glycerol plus 3, right? Fatty acid. We have lipids in form of fatty acids themselves. I can, right. We can have lipids in the form of cholesterol. We can have lipids in the form of cholesterol esters, which are cholesterol bound to fatty acids. Right. So I need to be able to absorb all of them somehow. So what do lipase do exactly? Right? What do lipase do? Right. That's what lipase do. So salivary lipase, pancreatic lipase, blah blah. What do? They are breaking down triglyceride into glycerol and three fatty acid molecules. They can break down cholesterol ester into cholesterol and fatty acid. That's what lipase do. So which means by the time I break them down to that molecule, I've broken them down to the simplest molecule for what absorption at that point. Because I don't think we have what? Do we have fatty acidases? That can further break down fatty acids, right? Do I have cholesterolases or something like that? No, right? So yeah, I've broken them down to the right absorbable form at that point. Okay. So next thing now, because these are what lipid soluble molecules, or some of them are polar molecules. They have the lipid soluble part and the water soluble part. Right, and you have a membrane that is what? That is lipid bilayer core. It's also amphipathic. That's the external surface exposed to the blood, polar, to the ECF, water, polar part, and it has the core, right? Yeah. So right, so we need to. So that's why we need to create what? We need to create what? Micelles, right? Micelles are basically we package, right, or arrange all those lipid molecules as well as lipid soluble vitamins, any other lipid you can think of, in a form where what the core is what is water soluble, and then the core is lipid soluble. We hide to hide the lipid soluble core from the what water soluble, right, exterior. So the polar part of those molecules will be on the outside, forms the surface of the micelles, and then the lipid soluble part forms the core of the micelles. And then those micelles can easily, right, travel across the membrane of enterocytes, right, and enter the what? The lumen, the cytoplasm of the enterocytes. Yeah. What do I need to form those micelles properly? What do we need? Thank you very much. That's why we have bile acids and bile salts. They play a role in properly, right, forming those micelles. Okay, so let's recap. What do we have so far? Lipid absorption. I have my lipases. I need lipases. Some salivary gland, the major ones from the pancreas, pancreatic lipase. We need bile, right? Bile acid and bile salts. And then we need what? An intact mucosa, right? Now, when we get into the cytoplasm, we now form what? We're going to form another lipoprotein, which is what? Chylomicrons. We're going to package all those micelles and their lipids and gold, package them in form of chylomicrons, which is a lipoprotein, attach B48 on it, and then we release it into what? Into the lymphatics, right? The lacteals, the lymphatics. And lymphatics will carry it, right? Through the thoracic duct all the way into the what? Into the venous circulation, right? Yeah, it's gonna end up in the jugular vein on the left side. Yeah. And that's how they enter the systemic circulation. That's why immediately after eating, if you operate on a patient that just ate, like a fatty meal, you're gonna see those lacteals, right? Yeah, they're gonna be dilated and distended. You can see them visibly. If you operate on a patient that just finished eating, you're gonna see all those lacteals and the lymphatics, right? Like flowing and distended. They are filled with lipids. Yeah, being absorbed actively in that patient. So, what can go wrong? I mean, a lot of things, right? What can go wrong with lipid absorption? A lot of things. So, a patient coming with steatorrhea, they can't absorb lipid. fatty stool, etc. Right. It could be lipase deficiency, something wrong with the pancreas, pancreatic insufficiency. There's no pancreatic lipase. Biliary tree obstruction can cause steatorrhea because we need bile. Here is not making liver cirrhosis. One has liver disease, they are not making, liver is not making bile. Or liver is making bile, the bile cannot be released by the gallbladder, right? Gallbladder paralysis. Or there's obstruction in the biliary tree, common bile duct or pancreatic duct. Yeah, that leads to steatorrhea. Or problem with what mucosa of the enterocyte. Right. And there are tests we can do to know that. You see what we did for glucose, we can do it in that patient. When we talk about the saccharide absorption, we can do it. We can do those tests. Give them a monosaccharide and see what happens. If I detect the monosaccharide in the blood and less in the stool, I know it's not a mucosa problem. Right. If I cannot see the monosaccharide in the blood or there's monosaccharide in the stool, I know the problem is a mucosa issue that is causing the patient's fat absorption, malabsorption. You're thinking celiac, Whipple, small bowel bacterial overgrowth, things like that. If I rule out mucosa issue, I check stool elastase, pancreatic elastase. I don't see it in the stool. Then you know likely pancreatic insufficiency. Or I give the patient disaccharides, give them polysaccharides. They can't absorb polysaccharide, likely pancreatic amylase, right? It's deficient. Yeah. You know it's pancreatic insufficiency. Oh, patient was able to absorb polysaccharides. There's no polysaccharide in the stool. There's no monosaccharide in the stool. Mucosa is fine. Pancreas is fine. Elastase in the stool is normal. So pancreas is fine. But still they have steatorrhea. I'm taking likely biliary tree at that point. Like primary sclerosing cholangitis, primary biliary cirrhosis. All those things that cause like stricture, right? Of the biliary tree. So you can see, so we're going back and forth. Physio but anatomy, location, function, function, location. Yeah. Finally, last but not least, proteins. What types of proteins do we have in our diet? What types of protein, not the enzyme now. What type of protein? So we can have proteins from amino acid. Those are the basic block, building block right, of protein. So in the form of amino acids, what else? Dipeptides, two amino acids, tripeptides, three amino acids, tetrapeptides, four or more. So anything above three, now polypeptides. And then proteins are more complex in the form of they are basic polypeptides that are formed of like quaternary structure, right? Right, and stuff like that. Those are ones called like proteins. But by the time the protein is eaten and gets through, right, digestion starts with the it starts in the stomach actually because gastric acid can denature protein. Then pepsinogen, right, we convert to pepsin, which will start the digestion process of the proteins and the polypeptides. And then it gets to the small intestine, we have now the trypsin, chylotrypsin, etc., right? And they're going to what? Further break down the polypeptides in the lumen into what? Break them down to what? Dipeptides and tripeptides. They can't break them down to amino acids. They're going to break down at the smallest structure, trypsin, pepsin, chylotrypsin, etc., right, will break down polypeptides down to or proteins down to be what? Will be dipeptides and tripeptides. Now, what do we need next? Now, we now need what? The dipeptidases and tripeptidases. Where are those ones located? On the mucosa. Just like we have our disaccharides, the disaccharidases, right, on the mucosa. The dipeptide peptidases and tripeptidases are on the mucosa. They are made by the enterocytes and embedded on the mucosa, as well as an enzyme called enteropeptidase. You know enteropeptidase, right? It's the one that actually triggers, right, the cascade of activation of those pancreatic enzymes. It's going to activate trypsin to trypsin. And trypsin will now activate the other enzymes. Yeah, pancreatic enzymes, right? Yeah. So they're on the mucosa. So which means that what? That's another way to tell me, right? To kind of determine the level of pathology, right? If someone is having malabsorption, where is the problem? I can either I'm using the carbohydrate pathway or I can also use the protein pathway to tell me where the problem is. You give the person diet that is rich in only dipeptidase, in dipeptides and tripeptides, and they can't break them down and absorb them, then I know there's no tripeptidase or dipeptidase on the mucosa. So it's a mucosa issue in that patient. Patient can break down dipeptides and tripeptides, but they cannot break down the larger proteins, polypeptides and proteins. Then likely there's no pepsin, or the pancreatic enzymes are not being released, or the enteropeptidase itself is deficient, it's missing, it's not being made, which is the one that activates the other enzymes from the pancreas. So having that logical approach in your mind, there's no you can kind of just figure, okay, right, this is what is not being absorbed, this is the location of the pathology. This is where the pathology is. I go to my options, I'm picking an option in line with that. Yeah. And then how are the amino acids absorbed? So break down the di and tripeptide peptides into amino acids. How do we get the amino acids into the blood? How do we absorb amino acids? Right. So just like SGLT1, there are co-transporters, right? That depend on sodium gradient that also absorb, right, amino acids. So same thing like the PCT, right? Yeah, proximal complex tubule. The way the kidneys reabsorb glucose from the urine, from amino acid in the PCT, etc., right? It's what happens, right? Also, right, in the small intestine. Yeah, same principle. Secondary active transporters for amino acids. Amino acids, how do you get them into the blood? How do you absorb them? Secondary active transporter, right? Just like glucose is absorbed and galactose, right, by SGLT1. Amino acids also have a sodium dependent, right, transporter or co-transporter. Yeah. Hmm. Questions? Questions? How do you treat pancreatic insufficiency? Giving the patient what lipase, right? Like pancreatic lipase, like when they eat or whatever with their food. So, what what is concerning about that? What should you like? What do you think can go? Okay, let me put it this way: a patient is getting pancreatic lipase, right? Supplementation, and they are still having diarrhea. It's not working. Why? What could explain that? I mean, lipase work on the lumen, right? It doesn't use the receptor. Patient is getting taking pancreatic lipase with every meal religiously, but still, it's not working. They're still having steatorrhea, etc. They're not absorbing lipid properly. Why? Where will the lipase go through? We know where it's going, where it's going to work, but where will it go through? I give pancreatic lipase orally. Where will it go through before it gets to the small intestine? Right. Why is that concerning? Exactly. Why is duodenal secretions, pancreatic secretions, and as well as duodenal secretions, why are they alkaline? Because the enzymes that work there work best at what? Alkaline pH. Yes. So I'm giving somebody oral pancreatic enzyme supplementation. The enzyme has to go through stomach, which is acidic. The acid can denature the enzyme. If it gets to the small intestine, it's not going to work by the time it gets to the small intestine. That is why, that is the concerning, right? That's the concern, right? In that scenario. So what can you do to minimize that possibility? Yes, suppress gastric acidity. Give PPIs and right. PPI, right, in that patient, combine the medication with PPIs to decrease gastric acidity. Yeah, that may help. Mhm. There are also drugs. There are a lot of drugs. Even you see, gastric acidity. There are a lot of drug interactions, right, at that level too. Like there are drugs that require acid for absorption, proper absorption. Drug like iron supplement. Iron requires acid for absorption. Iron, B12, they require acid for proper absorption. So somebody getting iron supplementation, B12 supplementation, um, medications, certain medications still require acid. I can't remember all of them offhand, but I think aspirin does require a gastric acid for absorption. And there are others too that require gastric acid for absorption. There are even other elements besides iron too. I think magnesium and calcium, they require acid for absorption. So patients that would undergo maybe gastric bypass surgery, where the gastric acidity is decreased, or undergone vagotomy, or is taking PPIs chronically, anything that suppresses gastric acidity, or they have what's the name? Pernicious anemia. Right. In pernicious anemia, we destroy the parental cells, right? So no acid. All those things, right? They are at risk for iron deficiency, B12 deficiency, calcium magnesium deficiency. If they take medications that require iron absorption, which I want you guys to check up, right? Those lists, yeah, those medications will not work. They require acid. They're not going to work. They won't be properly absorbed in those patients. Yeah. So drug-drug interaction at that level. All right. Anything else about GI physio? All right. I mean, we can talk about more relevant physio under pathology, so which Shani will tell us tomorrow. So, is one not GI part? Oh, oh, yeah, yeah, yeah. That's right. Yes, 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 yes. Tomorrow is biostat. Tomorrow is biostat, right? Biostat and what did we do this week? Endocrine and GI. Yeah, questions. Okay, yeah, that's true. Rosie, you want to say something? Bilirubin is on. What is bilirubin? Is bilirubin so? Question: what is bilirubin? What is bilirubin, bile acid, bile salt? Are they the same? Are they different? What is bile? So what is bilirubin? Exactly. So when you have that in your mind, you're thinking of something entirely different. It is related to red blood cells, hemoglobin. If I break down the porphyrin ring, right? I make what? I make biliverdin. Biliverdin becomes indirect, right? Bilirubin or unconjugated bilirubin first. Then what do you do with that unconjugated bilirubin? Because unconjugated bilirubin is lipid soluble, right? Lipid soluble, it's difficult to excrete out of the body. Yeah, sometimes lipid soluble, it won't leave because yeah, it's gonna keep getting reabsorbed back into the blood. If it's filtered in the urine, it's gonna make its way back into the blood since the membrane are basically lipid membranes can just enter freely. It doesn't need a transporter. So it's difficult to excrete unconjugated bilirubin or indirect bilirubin. So once it's made, typically in the spleen, which is where we break down red blood cells, yeah, by splenic macrophage is going to be made there and then enters the blood. Albumin will pick it up. It's going to bind to albumin as a transporter, right? Take it to the what? To the liver. The liver takes it up, hepatocytes, and they conjugate it to direct bilirubin, which is water soluble, easily excretable, right, out of the body, and then they're gonna secrete that direct bilirubin into what? Into bile, into the biliary system. So direct bilirubin is part of component of bile. Bile is like a fluid that contains multiple things, which includes direct bilirubin, cholesterol, bile acid and bile salt. Because bile acid and bile salt themselves we make from cholesterol. We make bile acids from cholesterol and then convert it to bile salts too. Yeah, but we make them from cholesterol body, right? So bile contains cholesterol, contains direct bilirubin, contains bile acid and bile salt, contains phospholipids like lecithin. Yeah, contains ALP, alkaline phosphatase, which is made by the epithelium, right, of the biliary tree. Yeah, so that's bile, right? So if I see problem with right, so direct bilirubin, the only thing that so what's the component? So once direct bilirubin is in the bile, what do we need it for? Okay, we need to excrete it out. That's why it's in bile. But then it also contributes to what? The color of stool. So once it gets in the lumen of the GI, it's going to be converted to what? Direct bilirubin converted to stacobilin, gives to the color. Then some of the direct bilirubin can enter the blood since it's water soluble. Enters the blood, end up in urine, gives urine, right? The color, urobilin. That's where the usefulness of direct bilirubin ends. If it's actually useful anyway, at that point, it's excluded, yeah. But then bile acid and bile salt, their usefulness goes beyond that now. We need them for fat absorption. And then cholesterol is excreted in bile. Also need to excrete cholesterol out of the body. So excrete it in bile. So the phospholipids in bile, they are meant to keep cholesterol what? As well as the bile acid and bile salt to keep the cholesterol soluble in bile. So that it doesn't precipitate, right, and form what? Stones before it can get it out of the body. Make sense? You get it? Excellent. So if I say hyperbilirubinemia, what can go wrong? Or what does that tell me? I say hyperbilirubinemia, what should I be thinking about? Oh, right, red blood cells, something is wrong there, or the liver, something is wrong there, or in the biliary tree, something is wrong. Yeah, because that's how I process bilirubin. till I get it out of the body. So red blood cell, liver, or biliary tree. That's what you're going to be thinking. Then, since I know the first half of that pathway is mostly what indirect, and the second half of the pathway is direct, and the middle, which is the liver, is a mixture. Basically, has both of them. Indirect enters, then becomes conjugated to direct. Then, if I see predominantly indirect hyperbilirubinemia, I'm thinking pre-hepatic pathology. Increase hemolysis. I'm destroying red blood cells too much. I'm destroying hemoglobin too much. Hemolysis. Or there's a defective transporter on the liver can't take up indirect bilirubin. How will I know which is which? Look at hemoglobin, because I'm going to give you CBC, right? So I check hemoglobin is normal, then it's a liver problem, it's a transporter problem. The liver can take up indirect bilirubin. But I see indirect bilirubin, and the hemoglobin is low. Then it's anemia, it's a lot of anemia or hemolysis going on. If I see direct hyperbilirubinemia, bilirubin is high, I check total is high, I check direct is high, is more than half of total. So it's mostly direct hyperbilirubinemia. Then it can be either the liver problem or where? Biliary tree. Liver problem being the liver cannot get direct out after conjugation. Or there's obstruction in the biliary tree that's preventing what the excretion, right? Of bile. Right. So now I have different differentials in my mind at that point. If I see mixed, both are high equally, likely liver. Since liver is where they both meet, kind of, yeah. So liver pathology can cause actually mixed, where both direct and indirect are both high, likely liver problem, primary liver pathology like hepatitis and stuff, hepatocellular liver injury, liver can't conjugate properly, or it's conjugating and it's being destroyed and the direct is spilling out. Yeah. So, right. So location, function, everything matters. The reason I want to know where those things are taking place or just have an idea of the location is I can